Hi everybody, it's Miss Pasega. By the end of this lesson, you should be able to tell me just a little bit about the support force. The support force is also called the normal force. You should be able to give me a good solid definition. Tell me where this force comes from, tell me how big it is, what direction it acts, when it occurs, and basically how it behaves. Right? So, to start us off, definition. The support force is the supporting force that acts between two solids. Now it has to be solids because solids have a different, they have different properties than fluids. It's the supporting force between two solid surfaces that push one another. Fluids, if I put a support force on a fluid, will tend to flow around it because they have other forces like adhesion and surface tension that are going to act differently. So we're only concerned with the support force. That's the force between two solid surfaces that push against one another. And the way you want to think about this is if you have your hand like this, and it's holding up a ball, the support that your hand gives the ball keeps it from falling. Now, like I said, it's also called the normal force. In every other physics textbook, except the one that you and I use, it's called normal. Because if I were to look at my hand versus the ball, the normal force works at a 90-degree angle. The word normal in math means 90 degrees. So if you were taking any other physics course, you would literally read this force as the force that supports two solid surfaces at a 90-degree angle from the surface, which we'll get into more in a second. Now correct me if I'm wrong, but there are only 4 universal forces and the normal force wasn't one of them. In fact, the 4 universal forces were gravity, weak nuclear force, electromagnetic force, and strong nuclear force. Well, it certainly doesn't come from gravity. The weak and strong nuclear force, well, you and I don't experience them because we're not at the nuclear level. We don't experience them very often. It must come from electricity and magnetism, which is a little bit strange. But I want you to think about the ball resting in my hand again. Here's the ball, and on the inside, the ball is made of atoms, with a proton in the center, or a positive nucleus in the center and a negative electron cloud on the outside. And remember, the nucleus is shielded. It's got all these electrons on the outside. So that if I were to look at the ball from a molecular perspective, it just looks like a bunch of electrons. So when my hand is here, the electrons in my hand, which are paired up with their little proton pairs, repel. That means the ball gets pushed up, and actually my hand also gets pushed down. Okay, now the really cool thing about this is that because it's repelling, the ball never really touches your hand. In fact, there's always going to be some distance between any two objects that are solid. So if you want to feel really depressed about your life, you never really touch anything. Right? Before you get a chance to touch anything, the electrons in the ball repel the electrons in your hand. So you've never actually given your mom a hug, and you've never been kissed. Right? You've never pet your own dog. You've never touched anything because before you have physically touched it, the electrons in your hand have repelled them. Right? But to be fair, when you feel that repelling force, you do actually sense it with your nerves. So you feel the touch, but you've never actually touched anything. Mind blown. So, in short, you never really touch anything. But the normal force happens when you bring two solid objects within a close enough distance to each other so that there's pressure between them. The tricky thing about the normal force is it can sometimes act in directions you don't expect. Like when a book pushes down on a table, the table pushes back. That makes sense. So it looks something like this. The electrons in the table repel the electrons in the book. So the normal force forms a right angle with the surface of the table. We totally expect that. That's totally normal. No pun intended. But once I get things like the skier going down the hill, I have to pay really close attention to what forms a 90-degree angle here. So what I'd like you to do is on your picture, draw this in with me. Draw a dotted line for the surface. Now draw a line 90 degrees to it that goes through the skier. Right? If you get stuck, you need to use like a protractor or something to draw a proper 90-degree angle. Go right ahead. The normal force has to be along this 90-degree angle, and it has to point away from your object. See how this normal force doesn't point down towards the table? Well, that's good. This normal force can't point down towards the ramp. It has to be pointing away, and if you think about it, that makes sense because the electrons are being repelled. Electrons repel electrons. It's always going to push away. Same thing with a box sliding down a ramp. Draw a dotted line for the ramp, the surface of the ramp, and draw a line perpendicular to it. The normal force is going to start from the center of your object and point away so that it forms a 90-degree angle with the surface. So if you wanted to write down a really good rule, the rule is that the normal force forms a 90-degree angle with whatever surface. But hey, this guy doing wall sits over here. He actually has two different surfaces. He's got a surface he forms with the wall. Let's draw that one in. Here's my dotted line. Here's the normal force. I'm going to use this dot as his center of mass because of the way it's distributed. So here's his normal force that's pushing away from the wall. The wall repels the electrons in his body to the left. Now, the other trick is that the floor isn't being shown in this picture, but the floor is pushing him up, right? So the floor pushes him up like that. He has two normal forces acting on him because he's touching two different surfaces. Same with this ladder. The ladder is touching the floor pushes it up, and touching the wall pushes it out. Okay? So it's always going to push away from the surface. So if you want to write down a good rule, the normal force forms a 90-degree angle with the surface and points away from it. Okay guys, quick and easy demo here. The support force is going to be just as big as the amount of pressure that's put on your scale. So in this case, read it out. The support force here, this is reading 499.6 grams. Or really, if I convert this over to newtons by multiplying kilograms by 9.8, this is about 0.5 newtons. Right? So if I apply a force, putting tension on my weight here, if I pull up, what's happening to the scale? Should look like it's decreasing, right? That's because the normal force is reactionary. The more I pull, the less it's there. So if I pull up, it's going to go down to 0. See? Not touching it, scale reads 0. But if I push down, let's say I, instead of using a spring scale, decide to mess with my scale a little bit by applying a force on the top. See, now it's going up. My normal force reacts to the amount of pressure put on it. So in short, if I push down, if I push down like this, it's going to increase the normal force because I've increased the pressure on the system. If I pull up, it's going to decrease the normal force because I decrease the pressure on the system. And if I just leave it to rest, the normal force equals the weight of this little block. Now notice this even works at an angle. If I push this at an angle, it's still increasing. If I pull it up at an angle, still decreasing. So don't worry about the angles too much. Even if it's on an incline, the amount of pressure that you put on an object is going to be resulting in that normal force. Finally, I come to one last problem. And this is a really important one because we've done this before, or you have done it in your life, and probably have never exactly realized what was going on. So, have you ever done this thing where you go up against a wall, something like this, and you push on an object, let's make it a book just so it's a rectangle. You push on it with your hand, and it doesn't fall down? That should be really strange to you, because let's think about what's going on here. The book has a bunch of forces acting on it. Right, if I draw the free body diagram, it's got gravity equal to the mass times the acceleration due to gravity of the book. I've definitely got a normal force from the wall. I'll call that normal wall. Hey, I'm being pushed by the hand. I've got a normal force from the hand. Force normal from the hand. And there's really one more force. If you think about it, these two are going to cancel. And as we've drawn it right now, the book should be accelerating due to gravity. Think about it for a second. Pause the video if you need to. What's the missing force? Did you figure it out yet? We had gravity. Check. Ooh, check. Normal forces. Check. There must be some other force. The normal from the ground doesn't cancel because the book isn't touching the ground. There's no air resistance because air resistance only occurs to moving objects. There's no tension. Gravity's working the wrong direction. So what force am I missing here? Nothing? Okay. There is a missing force here. And that force is friction. And if you want to see how it works, friction has the same magnitude as gravity. The only reason it works is because that friction force gets bigger when you increase the normal force. So if normal force goes up, force of friction goes up. That's why if you try to do something like lightly push a book against a wall, it doesn't work. It just starts to slide. If you ever tried to hold something up like you're trying to balance a bag of groceries while getting into a car, you'll find that if you put pressure on it between some other object, that it won't slide down the wall if you put enough force. That's because if your normal force goes up, friction goes up. And this is what we're going to get into next week. So I hope you liked the preview of all the good things that are coming towards us. Right? And have a great day.